Now down at the bottom, that's a picture of the shape sphere. Because a triangle has 3 sides, but its shape is defined by 2 internal angles, the great joy of shape dynamics is you can represent the first non-trivial problem visually, beautifully on the surface of a sphere. So each point on the sphere is the shape of a triangle. Mirror symmetric triangles are with the same are at the same latitude, are in the northern and southern hemisphere. The collinear triangles, the limiting case of collinear triangles, are on the equator, and there are 6 special points. There are 3 points, binary coincidences, where 2 particles get literally coincide or get very close to each other compared with the third. And then there are 3 other points which are called the Euler configurations, and I'll explain why in a moment. And they are saddle points of the complexity. The complexity is shown by the shading there. Now, in the 3-body problem, the complexity always has an absolute minimum at the equilateral triangle, whatever the mass is. And then it has 3 saddle points on the equator, these Euler points. And the complexity rises to infinitely high peaks at the 2-body collisions. So now the complexity, I'm going to stick my neck out. I think the complexity might just be the secret of the universe. Now that's a big claim, but I'm going to argue why. Well, first of all, and this is why we call it the complexity, is it's a measure of clustering or variety. Simon has mentioned our joint enthusiasm for Leibniz. Leibniz was always saying, variety is the only way you can sort of say anything about the universe. If there's no variety, you can't really say anything. So it's very fundamental at the epistemological level. You've already heard that it's minus the dimensionless shape potential. Now, this is a thing which is very interesting, is that it's the intrinsic size of any shape. Because how do you measure something? You take a ruler and you say, this is my unit of length. And now I lay it on the thing I want to measure. So going across the desk, it's about 5 times my ruler. So you measure a longer interval with a shorter interval. So what is the scale invariant size of a cluster of points? We'll say they all have equal mass. Well, you just divide the root mean square length by the mean harmonic length, and that is the scale invariant size. So I'm just going to illustrate that on that basis. So we're inside the universe. We have to measure, the size of the universe is measured relative to me. And if it's a universe of just 3 particles, this triangle, despite appearances, is actually smaller than that one, because the ratio of the shortest side to the longest side is greater in that one than that. So you have to get rid of the notion of size, and it's incredibly difficult to do it. Now, Poincaré pointed this out, how mysterious it was, but what he didn't consider was what happens when the shape changes. That's when things get really interesting. So just to bring the point home, compared with those 2 universes, they are tiny compared with this. This is vastly bigger than those for Alice in Wonderland creatures who live inside this universe, because that side is much shorter than that side. So get that into your minds. That is how you measure the size of the universe. Now, interestingly, this is very strange, because the principle of least action and the whole of both Newtonian and Einsteinian dynamics, you specify a ratio of sizes at the 2 ends of the integration of the action. So why on earth, when actually there's an intrinsic notion of size in a shape, does it play such a fundamental role in both Newtonian and Einsteinian dynamics? And finally, this quantity, it's a pure number that characterizes the whole universe in a way that the Planck units don't, because they rely on a particular choice of units. So there's something very fundamental about it. Now, the complexity is actually what defines the arrow of time. I'm going to assert that it's the complexity of the evolving universe, not entropy, which fundamentally determines the direction. The entropic arrow of time is a subsidiary one, which comes out of something I'm going to point out now. So if the energy is greater than or equal to 0, and in a Machian universe, you're going to expect the energy to be exactly 0, then except in zero measure cases, which I'll come to and are very interesting indeed, the size of the universe, the Newtonian universe, in the infinite Newtonian past, the moment of inertia is infinitely great. It comes down to a finite minimum and then rises to an absolute, goes up to infinity again. And that was discovered by Lagrange in 1772. The proof is done in two lines. It's a very simple proof. And that has very profound consequences. First of all, because the dilatational momentum, is the time derivative of the size of the universe, the moment of inertia, that's monotonic. It goes from minus infinity to plus infinity in either direction of time. And that means there is no Poincare recurrence. Now, Poincare recurrence is the real reason why Boltzmann could not explain the entropic arrow of time. It was Poincare recurrence in the famous debate with Sermolo. So, and that was because he presupposed a system in a box, which had a phase space of bounded Liouville measure. The Newtonian n-body problem does not have a bounded phase space. It has an unbounded phase space. The way you should think about statistics and the arrow of time is completely and utterly different in the Newtonian n-body problem, and I strongly believe it is going to prove to be so in the case of the universe described by general relativity. So what happens? So this is a plot of what the complexity does. This is a simulation, a numerical simulation with 1,000 particles. The dip at the bottom is around at this, what we call the Janus point, and there are bidirectional arrows of time that go out in both directions from it. And they are a direct consequence of the law of nature. That is not a past hypothesis assumption just put in desperately to explain the arrow of time. It is there straight as a consequence of Newton's laws of motion. There's no nonsense about that. And on the right, down below, you see a sort of an artistic impression of what is happening. At the Janus point, typically, the particles are moving around rather randomly, and they make a uniform thing, rather like a swarm of bees. I think that can be proved rigorously. It's a delicate proof, but certainly there's a lot of evidence that that's the case, and certainly there's a vast number of solutions where that happens. And then as you go out in both directions from the Janus point, clusters form, including above all Kepler pairs, which become absolutely perfect, ever better rods, clocks, and compasses all in one. And all those clocks that form out on either side from the Janus point, they all march in step. They're all in phase with each other. You go from disorder at the Janus point to ever better perfect order as you go out. This is the complete inversion of the normal story of the universe going from order to disorder. And it comes straight out of the Newtonian n-body problem. Now, where entropy comes into this is when subsystems form, because the mere fact that the complexity is increasing says that subsystems are forming. And as they form with a lower, and they exist transiently, they come into existence and they go out of existence, and that birth and death is aligned with the growth of complexity. And while they exist, they are subject to the virial theorem. They virialize for a certain length of time, and then they are like thermodynamic systems. So thermodynamics is emergent in this story. It's transient in systems that form transiently. So that's quite a big change in the picture. So the way really to think about Newtonian theory is to take scale out of it. You can solve the Hamiltonian constraint for the size of the universe, and then you just get something which is expressed in terms of shape degrees of freedom. There's one extra one because of that one extra one that comes in through the Newtonian theory. So the evolution in shape space is determined by the shape, the direction in which the shape is changing, and one extra degree of freedom. And it's a degree of freedom which Leibniz would love this. It's putting a striving into the universe. The universe is always striving to bend away from the natural geodesic in shape space and climb up to higher complexity. And you see it in this diagram here. You see the Janus point, you may not be able to see it, is a white square at the back of the shape sphere. And then the two branches of the solution go off in opposite directions. And you see how they climb up that mountain of the complexity. And as they go up there, that's where a Kepler pair forms. It's a Kepler pair forming and a singleton going off in the other direction. And relative to the clock, rod, and compass that the Kepler pair forms, the singleton is going off and is obeying Newton's first law. So it's an absolute perfect example of order being created out of chaos. And if you try and set up the solution and run it back from where the Kepler pairs formed, when it gets near the Janus point, that's a total scrambler. It becomes chaotic there, and you can't tell what will happen on the other half. But you know, if the energy and the angular momentum are zero, every single solution, except for this zero measure set to which I'm coming, will be forming a Kepler pair and a singleton. So I do love this expression, WYSIWYG. What you see is what you get. So there in that picture that you see there, that is the deep truth of Newtonian theory. It is completely wrong to say that Newtonian theory is a theory of clockwork that made it so hated by people like William Blake. It's not clockwork, but it's the creation of order out of disorder. And that order includes the creation of rods and synchronized clockwork. So it doesn't just describe clockwork, it describes how the clockwork is created and then continues to describe how that clockwork runs once it's been created. So as I say, it's a classic example, I would say, of Leibniz's idea that the universe is striving.